we've seen that phi is not quite an operator. It's an operator-valued distribution. In order to build your stress energy tensor, you've got phi squareds, derivatives of phi squareds, and so on. So what you have here is products of distributions, operator value distributions, operator value distributions. Products of distributions are not well defined in general, and so you've got issues here. So this will lead to divergences, and this is what plagues quantum theory all the time. And that's what we have to find, all these divergences. So the next section is renormalization. That's how we're going to find, again, three divergences. And that's the origin of this section 2 to renormalization. Remember, we're still doing flat space-time. A lot of this carries over without a hiccup to curve space-time. Plagued with divergences, and this really comes from the fact that you've got products of operator value distributions. Products of distributions, and that's not well defined. Let's see this explicitly. Let's do this explicitly for the case of the real scalar field in flat space-time using the UK complete set. To be honest, I'm not sure what to consider any field theory different from the real scalar field theory. So by default, that's what we use. So we quantize the Hamiltonian. The Hamiltonian now is an observable, and so it's an operator. So one way is you can write it like this. Where there is an ambiguity in the ordering that you choose in going from the classical theory to the quantum theory, which is crucial, and I'll explain now what the right prescription is. But say a naive ordering is this one, which makes it puts an A dagger on the same symmetrically. And now I'm going to take the expectation value of the Hamiltonian in the vacuum state, in the constant vacuum state. So what I'm going to do is I want the creation operators on the left of the annihilation operators. So all you do here is you apply the combination relations. So this is just A diagram, A, plus the delta. So here you can already see the issue. What I want to do is rubbish. Okay, I want to do bad mathematics, just to explain to you and just to see what the issues are, and how we need to resolve them. But let me tentatively write this as one identity operator, and then in the delta you will have k minus k, and that just 0. Okay? And delta of 0, that's a bad thing. So this will give you this, and now I take the expectation value of the Hamiltonian and the Minkowski vacuum state, well, it is, by definition of the Minkowski vacuum state, it is annihilated by the A case. So the first term will give you 0. And so what you're going to get is this. Okay. So what are the issues with this? It's probably the worst mathematics you've seen in a long time. But let's understand why this is bad. This is bad. What's wrong with this? Okay. Well, distribution at one point is fine. The problem is, this is just not, this is not well defined, so this is bad. Any more issues?
The integral is infinite.
The integral is infinite. Okay, this is square root of k squared plus n squared. So you've got something that is not going to converge on large k. So this is what I mean by playing with divergences. We're going to have to find of many divergences. So let's see how we deal with this. So we have to deal with many divergences attacking us from many different angles, okay? And we're going to deal with them in different ways. We have to fend them off. First of all, we're going to cure this one. The way we're going to do this, we're going to place our system in a box, if you wish. We're going to place boundary conditions on the scalar field. That will get rid of the first one. So consider now periodic boundary conditions. So at some distance L, in the x direction, we've got periodic boundary conditions, and we impose same for at y, and similarly at z equals y equals periodic boundary conditions with respect to the x direction, the y direction, and the z direction. So remember, our most solutions, if you just look at the U case, they're just given by this. Okay, there's a general and a linear combination of these will give you a solution of the Klein-Gordon equation, and we want to impose that the first equation, so number one means that exponential of minus I omega k t plus I Lx plus y, sorry, kxl plus kyy plus kzz, that has to be equal to exponential of minus I omega kt plus I kx0 kyy plus kzz. Time dependence goes away, the y dependence, the z dependence go away, and so that tells you the exponential of I kxl is equal to 0, and so that tells you that kx has to be a multiple of 2 pi. Well, sorry, the kxl has to be a multiple of 2 pi. An integer multiple of 2 pi, and the same thing for 2 and 3. They tell you that ky has to be, kyl has to be an integer multiple of So, the field now is just like before, linear combination of the complete set, but now k, you don't have any, the k index is not continuous anymore, now it's discrete. Okay, so you have a summation over k, but now with m's in being integer numbers. And the UK's are given by this, where the normalization now accounts for the length scale element. And then the Hamiltonian is just the same as what we've written, but now instead of an integral, we've got a summation over a discrete summation. So let's look at the Minkowski vacuum energy density. So that's just the Hamiltonian, well, it's the expectation value of the Hamiltonian in the Minkowski vacuum state, but I'm asking for an energy density, so I'm dividing it by the volume. Of your box. And I'm going to take the limit as, the box gets larger and larger, so as we approach the standard flat space. So the sum over k now, you can write it as in this way. delta kx, delta ky, they're just 2 pi over L. Okay, this is, each one of these is just 2 pi over L. And we've got a box in Q, in K space, so of length side L. So this cubed. So what happens? This allows us to look at what this looks like for large L. So for large L, we still have L over 2 pi, well, L cubed. So for this is for large L cubed is the volume. So volume over 2 pi cubed. And then the summation, as L gets larger, the summation becomes an integral. So this is an integral over R cubed of d of dk. Okay, so let's go back to this. From here, we're going to get, well, first of all, 1 over v, then v over 2 pi cubed. The sum over k has become an integral over r cubed, as L goes to infinity. We've got an omega k here, and well, this will kill the vacuum state. AK of Minkowski is equal to 0, and also AK dagger of Minkowski. That gives you a one particle state of momentum k. Similarly here, we get exactly the same, and those are just normal, taken to be normalized to unity, and so this is just 1. The v and the v go away, and the omega k is omega square root of 1 square k squared plus m squared. Okay, so the first good thing, we've got rid of that variable delta cube 0. Mathematically discussed it. Fended off one of the divergences. But here we still have divergence. You can go to spherical coordinates in k space if you wish. So you can write this as k cubed. So you can write all of this. Instead of using Cartesian coordinates in k space, you can use spherical coordinates in k space. So you can write this as the radius, so k, so k squared, sorry, or the r squared, and then an integral in the angular direction, but this does not depend on the orientation of the vector. This only depends on the modulus of the vector. So you can just take the angular integrals directly. And so we've got that the energy density Okay, this divergence, okay, this would be the limit as, you know, some k final goes to infinity, upper bound k final dk, and then k cubed, which is obviously just k to f to the 4 divided by 4, and this goes to infinity. So here we have another divergence. This is a quartic. This is a quartic divergence in the ultraviolet limit. Okay, ultraviolet meaning large frequencies. So the origin of this comes from, we can look at this as coming from different ways. One is the one that I mentioned earlier on. The Hamiltonian is T00, the strange unit tensor. That's built from phi squared, so products of distributions, and that's not well defined at the point. You can also look at this as the ground energy of each harmonic oscillator being non-zero, and so you've got an infinite amount of harmonic oscillators giving you an infinite energy. So this coming from existence of an infinite number of harmonic oscillators, each with non-zero vacuum energy. Which is omega k over 2, or more probably from the finding it is an operator one distribution, and so phi squared and same point is not well defined. As an operator. Okay, so we've got rid of the first type of divergence. Now we have to get rid of these other types of divergence, which is an ultraviolet kind of divergence, and that's going to be the same in Kerr spacetime. Ultraviolet means large frequencies. Large frequencies are probing small distances. So that's the connection between same point, the two phi's being multiplied, two distributions being multiplied at the same point, corresponding to a large frequency divergence. So there is an easy prescription for dealing with this in flat spacetime. It's more complicated in Kerr spacetime. We'll deal with this in Kerr spacetime in the appropriate way whenever we get to it. For now, we'll deal with this in the standard way, which is normal ordering. So we remove these divergences in a physically meaningful way via a renormalization procedure. So in flat spacetime, all you care about is jumps in differences in energy, differences of energy in quantum states, different quantum states. That's not going to be true in Kerr spacetime. Whenever we have Einstein-field equations, the energy of the system will be meaningful because it's a source of gravitational field. And so we can't, it's not just differences of energy between states. The energy of a state has got its own proper physical meaning in that it creates the gravitational field. So we'll have to be a lot more careful when we include gravity and the acting field relations. However, in flat spacetime, all we care about is differences between states. So in flat spacetime, the infinite in the vacuum energy density cannot be detected. By measuring transitions between states. And so, renormalization, we're going to subtract the infinite that's coming from Minkowski vacuum. We'll just say that the renormalized expectation value in the Minkowski vacuum state is zero. That's our definition of renormalized expectation value of the strength of the Hamiltonian in the Minkowski vacuum state. Subtract away the expectation value in a certain quantum state. Okay. All we care is the difference between the expectation values into quantum states. Now, which quantum state do we use to renormalize the expectation value in any quantum state? We're going to use the Minkowski vacuum state. One of the reasons it agrees with experiments. There's a so-called Casimir effect which has been observed experimentally, and that's how you renormalize the energy in the Casimir quantum state, by subtracting away the energy in the Minkowski vacuum state. So experiments such as the Casimir effect, which I don't think we're going to do, indicate that such quantum states is the Minkowski vacuum state. So every time we calculate the energy, the expectation value of the Hamiltonian is sort of quantum state, we need to renormalize it, but the way we do it is by subtracting the expectation value of the Minkowski quantum state. And a totally equivalent way of doing this is so-called normal ordering. Normal ordering tells you that all you do is, whenever you go from the classical theory to the quantum theory, you put your annihilation operators to the right. Okay. So standard and equivalent. At least for our operators connected in the field. show you now why that's the case. Suppose that Q is got so suppose that Q is a quadratic operator. Then you can write it as in this way. So this column to the left and to the right means normal ordering. You can see some function. So now take the difference. I'm going to show this. Take the difference well, let me give you an example of this economy. If you take A dagger, A plus A dagger, the difference between Q and normal order Q is A dagger, A dagger. And now, what's the normal ordering of this? The normal ordering of this is, it tells you, you place the creation operators to the left. These are annihilation operators. Yeah, so the annihilation operators to the right, creation operators to the left. So this one is already in the left, so this one you leave it as it is. This one is not. You place the creation operator on the left. And so these two guys go away, and that's just the commutator between A and A dagger, which is it's delta. Well, the delta is just equal to 1 in this case, because it's got no superinstance. And that's it. Okay. So this is an example of this. And now what I want to show you is that normal ordering is equivalent to subtracting the expectation value in a vacuum state. Okay, so you take now I want to show you that this is the same as normal ordering. So this is in some state psi, and now I subtract the expectation value that in constant vacuum state. And I will use this equation, example, this equation star. So I rewrite the Q in this way. Psi normal ordering Q. C is just it's not an operator, so it can come out. Well, I can do the same thing for the other one, so that's Q normal ordering minus C again, and so this is just one normalization, this one normalization, and so this guy and this guy go away. What is this equal to? Why?
But you say that it's efficiency or the energy vacuum.
Sorry?
The energy vacuum state.
No. I said that the renormalized expectation value of the Hamiltonian in the cosmic vacuum is 0, yes. Well, yeah, sorry. Okay. Right. So it's equivalent-ish. So this is not a Hamiltonian, Q is not a Hamiltonian. So it doesn't. It's related to what you're saying, but it's not quite it, because Q is not a Hamiltonian. But it is the same, the idea is the same. So the Q is a quadratic operator on that field. And I'm placing all annihilation operators to the right. So in here, there's going to be an annihilation operator to the right. So that's going to give you 0. And you just get the sign Q. Okay, so this is the proof of what they said here, that they're equivalent. Okay, you can think of it as subtracting the expectation value in the Minkowski state for any quadratic operator Q, for the in particular for the Hamiltonian, but just not necessarily for the Hamiltonian. And subtracting the expectation value in the Minkowski vacuum state is equivalent to doing normal order, placing the creation operators to the left of the annihilation operators. So in particular for the Hamiltonian, the normal order Hamiltonian now is just given by this, and obviously this means that the expectation value of the normal order Hamiltonian in the Minkowski vacuum state is 0. Any questions about this or anything? So like I said last week, next week I can't do Wednesday, so can we find an alternative time for next week? I didn't have a lot, many times, but I do. So Monday I can in the afternoon, so that's Monday 14th, I can in the afternoon. Tuesday 15th, it's pretty bad unless it's very early in the afternoon. Well, 2 o'clock could be fine. So Tuesday 15th could be at 2 p.m. and Thursday could be any time. So, can anyone not make it on Monday afternoon? 2, 3, 4.
I can come if it will be.
Sorry?
If it will be, I can come. But not the best day for me.
It's not the best day for you. Which one of the 3 is the best day for you?
Monday, anyway.
Sorry?
Monday is the best one.
Does it not suit anyone Monday afternoon?
Monday is best. There is a class from Gion is giving a course on Tuesdays and Thursdays.
Right.
Exactly at noon.
No?
At 12 p.m. 12 p.m. Monday.
I can't at 12 in fact. It's kind of 12. But from 1 p.m. onwards. So what's the best time then? 1 p.m., 2 p.m., 3 p.m.? Any preferences? 2 p.m. Is that healthy time? Okay, so no lecture on Wednesday. It's going to be at 2 p.m. on Monday. I don't know at which classroom. I'm going to try to get this, but I don't know which one. I'm going to write it on the website. Remember, there's a website for this. I haven't written anything yet, but I'm going to put it up on the website. Okay. you.